Pre-calculus 2.5, zeros of polynomial functions. Today's objectives: use the rational zero theorem to find possible rational zeros, find zeros of a polynomial function, solve polynomial equations, use linear factorization theorem to find polynomials with given zeros, use Descartes' rule of sign change. The rational zero theorem. If f of x is equal to a sub n, x to the n plus, so if it's a polynomial, has integer coefficients, so those are whole numbers, positive or negative, where p over q is reduced to lowest terms. So in this case, here is our p, and here is our q. Oh, it says it later on. Okay, in lowest terms is a rational zero of f, then p is a factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. All right, so this isn't as bad as it looks, but let's just jump right on ahead. List all the possible zeros of f of x is equal to x squared plus 3x minus 4. All right, so they're just possible zeros. They're not necessarily the zeros. So we're going to do our p over q. So this is going to be all the possible factors of negative 4 is going to be our p. So that's going to be a plus or minus 4, plus or minus 2, and plus or minus 1. You can get a negative 4 by multiplying a positive 4 by negative 1, a negative 4 by positive 1, positive 2 by negative 2, etc. Likewise, we're going to have all of our possible zeros for our leading coefficient, which is actually just a 1. So that's just going to be plus or minus 1. All right, this one simplifies fairly easily. This just becomes plus or minus 4, comma, plus or minus 2, comma, plus or minus 1. So these are all the possible zeros. They're not necessarily the zeros, they're just possible zeros. Positive negative 4, positive negative 2, positive negative 1. Simple enough so far. All right, same thing. List all the possible zeros of this equation. So we're going to get p over q. This is going to be equal to, well, a positive or negative 2, a positive or negative 1, all over a positive or negative 3, and a positive or negative 1. All right, let's get all the ones on the denominator taken care of. So we're going to get a plus or minus 1, comma, plus or minus 2. So that was dividing both of these by 1. But now we're going to have something else here. We're also going to have plus or minus 1/3 and plus or minus 2/3 by dividing both 1 and 2 by 3. So yes, they are possible zeros. Our p's and q's have to be integers, but that does not mean our zeros have to be integers. So here our zeros can be fractions. All right, finding all the zeros of a polynomial function. Ooh, so we have 120. It's a big number. Okay, let's do it. P over q. All right, so we're going to have 120, and I'm going to put a 1 on the end. We can divide this by a 2, which gives us a 60. That was weird. 60. We can divide 120 by 3, and that'll give us a 40. We can divide 120 by 4, which is going to give us a 10. We can divide 120 by 5. Oh, it's not 10. 120 divided by 4 gives us a 30. I was dividing 40 by 4. Okay, now by 5. So I'm just going to use my calculator here. I'm not going to think about it. 120 divided by 5 gives me 24. And then we can divide it by 6, 120 divided by 6 gives me 20. And is there anything else? 8. I don't think we can do 120 divided by 8. Oh, we can. Okay. So we have an 8, and then over here we're going to get a 15. Wow, that is bad. And I think that's about it. I'm going to try 120 divided by 9. Nope. 120 divided by 7. Nope. Okay, so that's it. Whew, that's a lot of numbers. But the good news is they're all over plus or minus 1, so they all end up becoming this. Plus or minus. Here I'm going to put the whole thing inside of parentheses because I didn't write the plus or minuses, so that'll distribute. All right, so now we need to find what this is. Well, let's use some synthetic division. And let's try to get strategic here. So this is going to be a bit of guess and testing. So I'm going to try 5. Do a 5. So we're going to get a 1, negative 5, negative 26, and 120. May have needed a negative 5. So we get a 5. Gives me a 5 with a 0, 0, 0. Wow, what is up with my pen today? Oh, maybe it's touching my watch. Okay, that gives me a negative 26. And then what's 5 times 26? 130. So that's not a 0. Okay. I'm going to go backwards. I'm going to try now. Yes, I know, I'm erasing my work. Only because I don't have that much space. Let's try negative 5. So we get a 1, we get a negative 5, which gives us a negative 10. That's going to give us a 50. 50 minus 26 gives us a 24. 5 times 24, 120. What do you know? There we go. 5 was good. Just did the wrong one. So that means that one of our zeros was x equals negative 5. And now we're going to have an x squared minus 10x plus 24 equals 0. Remember, it's 1 power less. Let's see, 24. Do we have things that multiply to make 24 that add to become negative 10? And I think we do. Negative 4 times negative 6 gives us a positive 24. And it also adds to be a negative 10. So this can become an x minus 4 times an x minus 6 equals 0. So we get negative 5 as well as a positive 4 and a positive 6 if we set those all equal to 0. Do it. I'm not going to. You can. Pause. Try it. I dare you. Moving on. All right. Find all the zeros. Same thing, but different. Okay, cool. So, negative 7. That's going to be quite easy. P over Q is equal to plus or minus 7, comma, plus or minus 1. Once again, we have that Q, which is a 1, so I'm not even going to write it. So at least now, in doing our synthetic division, we only have 4 possibilities. Okay, so I see here that everything here has a positive except for the last number. So I'm going to try with a negative number. I'm going to try negative 1. So we're going to get 1, 12, 34 minus 7. What is going on? There we go. So we get a 1. We're going to get a -1, which then gives us an 11, -11. And I don't think that's going to work. 34 minus 11 gives me 23. That's not going to work. All right, let's try -7 instead. So we get a 1, we get a -7. 12 minus 7, I should be able to do that, but I'm not going to, is 5. Okay. 5 times -7 is a -35, which gives me a -1. -7 times -1 gives me a 7, gives me a 0. Oh, good day. Okay, so we're going to get x equals -7 is 1, 0. And then we get an x, wow, x squared plus 5x minus 1 equals 0. Well, folks, sad face. We have to use the quadratic formula. So a equals 1, b equals 5, c equals -1. So we're going to get -5 plus or minus square root of 25 minus 4 times 1 times -1 all over 2, or -5 plus or minus square root of, well, I get two negatives times with the 4, so I'm going to get a 29, which is a prime number, all over 2. So, yes, I skipped steps, pre-calculus, hashtag Crimea River. All right, pause, do the math. You can do it. That right there is 3 zeros, by the way. We have that power of 3, so we have up to 3 zeros. They are unique because there's the plus and there's the minus. Okay, solving another polynomial equation. Wow, it seems to be a theme today. Here we go. 24. So P over Q, that's the highlighter, is 24. We're going to get a 12. We're going to get an 8. We're going to get a 4. Nope, a 6, a 4, a 2, and a 1. Let's see. 1 times 24, 12 times 2, 8 times, so we missed 3. And then once again, all over 1, and it's plus or minus, so we have all those different possibilities. All right, so once again, I'm looking at this. I'm trying to see what's happening here. We've got some alternating signs. So I'm going to try a -1 over here. Oh, you can't see that. My face is in the way. There's the numbers. All right. The numbers tend to get bigger towards the end. I'm going to try a -2. You know what? No, I'm going to try a positive number. I'm going to try a +2. I'm just guessing here, folks. Don't think I actually know what's going on. Well, I know the math. I just don't know what the answer is. Okay, so I get a 1. Gives me a 2, which gives me a 4. Don't like it when my pen does that. Which gives me an 8. Okay, that then gives me a -5. 2 times -5 is a -10, which gives me a, well, that gives me a -24, but that's too soon because that's going to give me a -48. That's not our friend. Let's try a -2. So we get a 1, -2 gives me a 0, 0, -13. That's going to give me a +26. 26 minus 14 gives me a 12. Whatcha? Okay, here we go. So now we get a -24. So now we're going to get 1 power less, x cubed, plus 0x squared. You know, I'm just doing another synthetic division. So I'm going to go ahead and make another one of these backwards L's. I have a 12. I've got a 13. So if we wanted to, we could have our P over Q and kind of eliminate some things here. So we have plus or minus 12, 6, 4, 3, 2, and 1. That 3 is way too ugly. Let's see, 1 times 12, 2 times 6, 2 times 6, and 3 times 4. Okay, cool. So we have fewer numbers here. We don't have to worry about the 24, okay, and the 8s. So now, let's try positive 2. I'm going to put a positive 2 right here. We get a 1, a 2, 2, a 4. 4 minus 13 is negative 9. I don't think that's going to work. Okay. Well, that was not the winner. Let's try 1. That gives me a negative 12. And then look at that. It was a lucky guess, folks. So then now we're going to get x equals negative 2, positive 1, and now we have our x squared plus x minus 12 equals 0. Things that multiply to make negative 12 add up to become 1 is a 3 and a 4. But the 3 has to be negative. So we get x minus 3 times x plus 4, or we just get the answers of also a negative 4 and a 3. No, that's not in the correct order, but you know what? Tired of recording things. This is the third one I've done today, by the way. So, all right. Properties of roots of polynomials. I can probably turn my face back on for those of you who actually like to see that. All right. If a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. So that means that even if we get x equals 2 twice, that's 2 roots even though it's the same one. If a plus bi is a root of a polynomial equation with real coefficients, where b is not equal to 0, then the imaginary number a minus bi is also a root. Okay, so we have these complex numbers. They come in conjugate pairs. If we have one complex root, its conjugate is also a pair, another root. Just throwing that out there. All right, the fundamental theorem of algebra. If f of x is a polynomial of degree n, where n is greater than 1, so it's not a line, it's something more than that, then the equation f of x has at least one complex root. Complex roots. They might be real roots. They might not have imaginary numbers, but it's possible. All these different rules. Okay, linear factorization theorem. So basically what this is saying is that you can multiply all of your roots together. So if I have x equals negative 2, 0, and 1, then I can say that f of x is equal to some sort of constant a of n times x, that's the 0, times x plus 2 plus x minus 1. And we can find out what the equation is if we had more information about the a sub n. And maybe my pencil battery is dying. Maybe that's what's happening here. There we go. So that's all the fundamental theorem. The linear factorization theorem is saying is that if we have these zeros, we can write them as a bunch of linear factors. Cool. All right, let's combine a few of these together. So finding a polynomial function with given zeros. find a fourth degree polynomial function f of x with real coefficients that has -3, 3, and 2i zeros such that f of 1 is equal to 10. Okay, so first off, we have a fourth degree polynomial, but we only have 3 zeros. That's because we also have -2i as a zero. So we can say f of x is equal to a sub n, some number we don't know, times x plus 3 times x minus 3. Come on, pen. Just let me finish. Plus 3 minus 3 x minus 2i x plus 2i. If we paid attention to my, well, yeah. If we paid attention to my lesson on complex numbers, I think that was what, 2.1, then we know that this right here can just become f of x is equal to a sub n times x plus, it is a difference of squares. We'll just go ahead and do it. X squared minus 9 times x squared plus 4. Go back and look at 2.1 if you don't like this. And now we just need to solve for our a sub n. I'm not going to go ahead and distribute anymore. So here we're saying that when we plug in 1 for our x's, our y becomes a 10. We get our a sub n is equal to 1 minus 9 times 1 plus 4. Yes, I squared the 1's. Or that 10 is equal to a sub n times -8 times 5. Or that 10 is equal to -40 a sub n. Or a sub n is equal to a -1/4. So our actual equation is f of x, pen please stick with me here, is equal to -1/4 x squared minus 9 times x squared plus 4. We did it. We made it. At least to the end of the 12th of 14 slides. Okay. Descartes' rule of sign changes, or signs. Let f of x be a polynomial. The number of positive real zeros of f is either the same as the number of sign changes of f of x or less than a number of sign changes of f of x by a positive even integer, 0, 2, 4, 6. If f of x has one variation in sign, then f of x has exactly 1 0. Okay, so we're counting the signs here. If the signs don't change, well, okay, we're counting the number of sign changes here. The number of times the signs change tells us the number of possible real positive zeros there are, or less than it by a factor of 2. We'll do an example. The number of real negative zeros of f is either the same as the number of sign changes of f of -x, so we have to actually plug in -x, or less by the number of sign changes of f of -x by a positive even integer. So once again, 2, 4, 6 less. Okay, let's do this. Last example. We can do this. Here we're just determining the number of positive and negative real zeros. Possible number. Let's highlight that. We're not actually determining the number, it's the possible number. Okay, I'm going to write this down a second time. F of x. Actually, I'm going to do f of -x. No, I'll do f of x first. Equals -x cubed plus 2x squared plus 5x minus 6. Minus 6. So we're just counting how many times the signs change. It goes from negative to positive, so that's 1. And then it doesn't change again until we go to here. So now it goes positive to positive and then positive to negative. So there are 2. So there are either 2 or 0 real positive zeros. 2, because that's the number of sign changes, or less by an even integer. The next closest even integer to 2 is 2, so we'll subtract 2, so we get 0. All right, for the other one, we need to replace our f of x with negative x and simplify, kind of like when we were doing symmetry. So we get a negative times negative x cubed plus 2 times negative x squared plus 5 times negative x minus 6. We'll simplify and get an x to the 4th plus 2x squared minus 5x minus 6. So here we have exactly one sign change, so there are 1 real negative zeros. Okay, the E was my fault, but then the zeros was the pen. Okay, and that is all, folks. That's the end of the presentation.